So thanks, Gretchen, for the introduction, and I'm happy to be back here at the JQI and have this opportunity to talk about some of the things we've been working on at NIST. So I'll be talking about nonlinear resonators that we're trying to use for various purposes in both quantum photonics and also sort of time and frequency metrology. So just kind of, whoops, I forgot to plug this thing in, sorry. So just kind of generically, my lab is working in the area of nanophotonics. So for me, what this means is that we take advantage of nanofabrication technology to pattern materials at very small length scales. And this lets us control the dielectric function at those small length scales. And that in turn allows us to manipulate the propagation and confinement of light at the wavelength scale. So by having access to resources like strong field confinement and long photon lifetimes and optical resonators, and the ability to engineer the group and phase velocity with which light propagates through a system, we can strongly enhance light-matter interactions relative to what you have in typical bulk materials. At the same time, the nanofabrication technology that we're trying to take advantage of is in principle scalable and allows you to integrate different systems together into some kind of complex functional unit. So I think the upshot is that we hope that these devices both support kind of interesting physics that we can study, but then the platform is something that can be applied outside of a lab environment in some kind of application. So this is the kind of work that we've been doing in my lab since I've been at NIST. There's been a few different kind of project areas. We've been developing devices for generating quantum states of light. So these are both based upon single quantum dots as well as sort of parametric nonlinear processes and materials like silicon. We've been working with colleagues at NIST and Boulder to develop nanophotonics for metrology purposes. So there's a collaboration with John Kitching's group where we're trying to integrate single-mode nanophotonics together with atomic vapors for wavelength references. I'll be talking today a little bit about the work on microresonator frequency combs that we're using for things like clocks and frequency synthesis. We've had some applications of cavity optomechanical systems. So these are systems in which optical modes are coupled to mechanical modes. Our initial work was focused on trying to use these for developing kind of high bandwidth, high sensitivity force and displacement sensors. So for example, having kind of novel heads for atomic force microscopes. Our more recent work has been on using mechanics as a bridge between the radio frequency and optical domains. And then finally, we've been interested in this topic of quantum frequency conversion for some time. So this is the frequency conversion of a quantum state of light. And we're interested in this because it's a mechanism through which you can connect quantum systems that operate at different wavelengths. Kind of our initial work on this was in using some of the quantum dot single photon sources we developed together with kind of quasi-commercial frequency conversion technology. So things that we could buy from a company just to demonstrate proof of principle things like you can frequency convert single photon Fock states. But our more recent work has been in developing our own frequency converters based upon these nonlinear resonators, and that's what I'll be talking about today. So another way that I try and classify the things we do in the lab is in terms of the kind of light-matter interaction that we're trying to enhance with the nanophotonic geometry. So some of them involve the enhancement of the interaction of a single quantum emitter with a confined optical field. So traditionally you might think about this as the domain of cavity QED with trapped atoms or neutral atoms or trapped ions. In our case, the atom is basically a solid-state quantum emitter like a quantum dot. We've also looked at systems in which we enhance kind of acousto-optic phenomena. So you might think about things like Brillouin or Raman scattering in fibers. In our case, we're engineering these phonons basically using nanofabrication. And then we are also looking at systems in which we could enhance parametric nonlinear processes. So these are things like harmonic generation, right? For example, in this laser pointer, there's second harmonic generation. Or things like four-wave mixing that kind of seed the supercontinuum generation that occurs in optical fibers. And these are kind of the sources that you can buy in the lab now. So on the topic of kind of single quantum emitters, I'm not really going to talk about most of this, but what we've been doing over the last couple of years has been working with a few different groups and trying to develop efficient single quantum dot based devices where you locate where the quantum dots are initially using fluorescence imaging, and then you build your device around it. So we've had some collaborations with a group, Christian Schneider and Sven Hofling at the University of Würzburg, Peter Lodahl at the University of Copenhagen, and recently Stefan Reisenstein from TU Berlin. And these are all based upon just trying to create really good single photon sources with quantum dots. One thing I'll spend a little bit of time talking about today is how we can integrate those types of single photon sources based on quantum dots together with the Kerr nonlinear platform that I'm going to be spending most of my time describing. So I won't talk about cavity optomechanics at all. I know that there's maybe people in the audience who are interested in this field. So again, what we're looking at here is the interaction of kind of localized optical modes and localized mechanical modes. In our case, the mechanics is all at gigahertz frequency. That's kind of the vibrational modes of these engineered nanobeams. And what we're working on right now, for the most part, is using piezoelectric materials as sort of a natural way to connect radio frequency waves and optical waves through the mechanics, because piezoelectricity basically couples RF to strain, and optomechanics can couple that strain to optics effectively. We did have some nice experiments together with Tom Purdy and Jake Taylor. Tom really did a very nice experiment where he took one of these nanobeam cavities and he made a thermometer out of it, where basically the Brownian motion is calibrated to kind of quantum noise. So what I'm going to be talking about today, the real focus is going to be on these nonlinear and nanophotonic devices. So I'll be talking about how we can use these for quantum frequency conversion. We can generate kind of interesting photon pair sources. And we can develop microresonator frequency combs, which can be used for kind of timing and navigation type applications. So the specific nonlinearity that we exploit in our devices is the third order optical nonlinearity. So just to make sure we're kind of all on the same page, if we can describe a material in terms of its electronic polarization, which is its response to some applied electromagnetic field, then a third order nonlinear medium is one in which the leading nonlinearity is one that scales as this input field cubed. So what that means then is, because this nonlinear polarization basically serves as a source in Maxwell's wave equation, if you come in with fields at different frequencies, this nonlinear polarization is going to oscillate at the various combinations of those frequencies, and that allows you to generate light at these different combinations of the frequencies. So to give some specific examples, you have things like third harmonic generation. So you come in with a frequency omega p, and the third harmonic is generated, so 3 times omega p. There's four-wave mixing, so you have the scenario in which you generate signal and Euler photons whose frequencies add up to twice the pump frequency in the degenerate case, or equals the sum of the pump frequencies in the non-degenerate case. And then there's this four-wave mixing Bragg scattering, which I'll talk about. And this is kind of a frequency conversion process where you shift an input photon by a frequency difference that's set by 2 pump frequencies, by the difference in 2 pump frequencies. And so all of these processes, they have sort of a classical component to them, but they can also be viewed from the perspective of sort of quantum photonics. So if you look in the reverse regime of third harmonic generation, you can think about generating photon triplets. If you work in the spontaneous regime for either of these four-wave mixing processes, you can generate photon pairs. This frequency conversion can be either classical frequency conversion, or as we'll show, you can also frequency convert quantum states of light. And sort of one important point is that these third order nonlinear media are pretty common. The most common third order nonlinear medium is the optical fiber, and this is something that's been extremely well studied over the past few decades, four-wave mixing and optical fibers. But what the nanophotonics adds to it is you have different materials which can be more nonlinear. You have the ability to fashion resonators, which adds some new physics and some new functionality. And you have a strong ability to control dispersion, which allows you to phase match a number of different processes. So this is the specific kind of nonlinear platform that we're working with. So these are waveguides. The core is comprised of stoichiometric silicon nitride. It sits on top of a lower silicon dioxide cladding, and the upper cladding is either air or silicon dioxide. And this is really like a popular platform within the nanophotonics community right now. And some of the reasons are that silicon nitride has this very broad transparency window, so it goes all the way down to the UV and all the way up in wavelength to close to the mid-IR. And it has a pretty large nonlinear refractive index, which is proportional to the chi3. It's about 10 times larger than that of the silica glass that's in optical fibers. From my perspective, probably the most important thing about this platform is that you have a strong ability to engineer dispersion, and that allows you to achieve phase matching. So if we think about just kind of parametric nonlinear processes, you always need to satisfy kind of energy conservation or frequency matching and momentum conservation or phase matching. And so waveguides are structures that emit kind of a continuous range of frequencies. So typically the frequency matching is straightforward to achieve. You just put in the input fields at their appropriate frequencies and you can get energy conservation to work out. But what's generally hard to get to work out is phase matching or the momentum conservation. And that's because materials have dispersion. So light is propagating at different speeds as a function of wavelength. And so you need something to allow that to happen in order to make phase matching happen. And so typically in nonlinear optics, you think about using something like birefringence. That's something you can use, or you use quasi-phase matching, the ability to pull the material. But in these highly confined waveguiding systems, you can just use kind of a geometric effect, the waveguiding effect. And so what that means is that the fraction of the field that's in the core versus the cladding changes as a function of wavelength. And so this waveguiding dispersion can actually completely compensate for the material dispersion, and that allows you to flexibly phase match a huge variety of different processes. So what I'm plotting here in this graph is an illustration of this. This is a calculation of something called the dispersion parameter, and this is just related to the group velocity dispersion in one of these waveguides. So this is plotted as a function of wavelength, and the thing that's varying between these three curves is just the width of this waveguide. We're keeping the thickness fixed, and we're just varying the width of the waveguide by a few hundred nanometers. And so the overall point is that just by making small geometric changes to the system, you can really significantly alter this dispersion profile. And so that just gives some indication that you can really influence phase matching in these devices just through simple geometric control. And again, this stems from the fact that you have this large refractive index contrast between silicon nitride and silicon dioxide or air. And if you contrast this against optical fibers, you have a comparatively large refractive index contrast in this kind of device. Okay, so over the last few years, we've been interested not necessarily in four-wave mixing in waveguides per se, but instead we wrap these waveguides around into ring resonators. And so we need to think a little bit about how the considerations of phase and frequency matching apply in the case of these resonators. And so this is a so-called whispering gallery resonator geometry. And because of this kind of circular symmetry, this imposes some kind of constraint on how the electric field or the electromagnetic field behaves in this azimuthal direction. It has this e to the im phi dependence, where phi is this azimuthal angle and m is some integer index. So this is just saying that you have this boundary condition that allows the field to wrap on itself. But the reason why this is important is because the phase that we want to match in one of these resonators, right, the phase velocity that we want to match is that in the azimuthal direction. It's effectively sort of the angular momentum of the light. And so because we have this criterion on the modes, the phase matching criterion effectively becomes a kind of mode number matching criterion. So to give like a concrete example, for a process like spontaneous four-wave mixing, you annihilate two pump photons and you generate a signal and idler photon whose frequencies add up to twice this pump frequency. And so the corresponding mode number matching condition is just going to be that twice the azimuthal mode number for the pump should equal the azimuthal mode number for the idler plus the azimuthal mode number for the signal. So this is just the same thing as our regular kind of phase matching condition in terms of the phase velocities here, or the wave vectors essentially. But now we're writing it as this kind of mode number matching condition. So in practice, what this means is that you need to identify the modes with the appropriate azimuthal mode numbers that satisfy this criterion. And then you need the corresponding frequencies of those modes to be lined up appropriately to satisfy this criterion. And so in general, this is not going to happen. You're not going to have a resonator that any arbitrary resonator that does this. But this is where the dispersion engineering comes in that I was describing on the previous view graph. So just by engineering kind of the thickness and the width of the waveguide that comprises this ring resonator, you can simultaneously have both of these criteria occur. One caveat I should mention is that when I write out these frequency matching conditions, I'm sort of implicitly saying that this is an empty cavity, that there's no power inside the cavity. Once you put enough power inside the cavity, then you're going to have Kerr nonlinear frequency shifts, and those frequency shifts have to be taken into account. But you can do that, and you get a kind of a condition that just includes these frequency shifts, essentially. So in addition to getting the phase matching and the frequency matching worked out, the other sorts of things that you need to do is you need to make sure that you can get light into and out of the device with a high efficiency. So it's not just good enough to have good internal efficiency within the ring. You want to make sure that you couple all of your input signal into that ring. And when you frequency convert, you want to make sure you extract all of that output signal out of the ring. And then we also might need to worry about sort of competing four-wave mixing processes. So these competing processes might be sources of noise if you make a frequency converter, or these competing four-wave mixing processes might be a source of inefficiency. Your pumps are getting depleted by these unwanted processes instead of being used to convert your light that you care about. So you can actually simulate these systems pretty well. To first order, you can think about writing some set of coupled mode equations that takes into account the different frequencies, the different sidebands that are involved in your process. But when you do that, when you just write out some restricted set of coupled mode equations with a kind of restricted basis set, then you might not capture the full physics of the system. You might not capture any of these competing four-wave mixing processes. So you can think about expanding that basis set. And if you continue to do so, you end up with something called the Lugiato-Lefebvre equation, which is kind of a mean field approach for including a large basis of modes. And so what this Lugiato-Lefebvre equation is, it's basically Maxwell's equations in a third-order nonlinear medium, but specifically applied to the situation of a damped and driven resonator. So this is an example of the Lugiato-Lefebvre equation. It basically talks about or shows the sort of time evolution of the field inside the resonator, depends upon things like loss, detuning, the dispersion, nonlinearity, and driving. And so this looks very similar to other types of equations that one might write for describing, cavity QED effects or cavity optomechanical effects. There's kind of a different Hamiltonian, effectively. And so this Lugiato-Lefebvre equation is something that's really been heavily studied in the context of microresonator frequency combs in order to provide sort of quantitative predictions as to what the comb spectra are going to look like. But what we and other groups have recently shown is that you can apply the same LLE equation to other third-order nonlinear processes. And so we use it now in order to model things like our frequency converters and our pair generators. Okay, so the first sort of application of these Kerr nonlinear resonators that I want to talk about is this topic of quantum frequency conversion. So just to be clear, this is the frequency conversion of a quantum state of light, typically using a strong classical pump. So this is not like a photon-photon nonlinearity. It's not one photon that's frequency converting another photon. It's a strong classical field that's taking a quantum state of light and mapping it from one wavelength band to another. And so this has been of interest within kind of the quantum photonics community for some time. One of the main reasons why people have been interested in it is in trying to create a telecom band interface for visible wavelength quantum systems. So you have all these quantum systems that might be very good at storing quantum information, or they might be good at generating quantum states of light, but oftentimes they have transitions that are at the visible or maybe even the UV. So things like trapped ions or atoms or spins and nitrogen vacancy centers. So the issue is that those photons don't necessarily propagate over optical fibers with low loss. For example, if you look at the Thorlabs catalog at 1550 nanometers, you can travel over fiber, something like 15 kilometers before you lose half of your light. Whereas in the red, you might only be able to travel over a few hundred meters before you lose half your light. So having an efficient and low noise interface that allows you to go from your original wavelength down to the telecom band so that you can travel over long distance in a fiber and then go back to the original wavelength can be an important kind of resource. Several years ago, we also looked at some other applications of frequency convergence. So we looked at the scenario in which you have single photon sources that are at different wavelengths, and you want to make those photons quantum mechanically identical. So you can frequency convert them to exactly the same wavelength, and you can observe quantum interference. We also looked at the scenario in which this low noise efficient frequency conversion can be useful for detection. The idea here is simple. It's just that you maybe have a detector that doesn't work so well at a certain wavelength, so then you just frequency convert your light to a wavelength for which you have a better detector, essentially. Okay, so the vast majority of all the experiments that have been done that demonstrate this kind of quantum frequency conversion have involved systems that rely upon the second order nonlinearity. Go ahead, please.
What's the phasing formation at quantum coherence when you convert your frequencies to telecom for this?
No.
So you have your...
Yeah, so you retain that, and you can show. I'll show some experiments and so on. I mean, I'm not sure if we necessarily have an experiment I can show you where you can definitively say that the phase information is retained. But I think if you look at the sort of the Hamiltonian associated with this process, there's no reason why you wouldn't maintain that phase information. And in fact, you sort of have an additional degree of freedom because you can apply, for example, a phase onto your classical pump, and then through like a 3-wave mixing or a 4-wave mixing process, like that phase can get mapped onto the output quantum state of light. So you can do these things in a kind of a fully phase coherent way. So the point I was trying to get to was just that most of the experiments that have been done on this kind of quantum frequency conversion have involved Chi2 nonlinear media. So these are things like where you can have some frequency generation or difference frequency generation. But we were interested in the silicon nitride platform because silicon nitride is a material that's very widely accessible. Almost any clean room in the country will have some ability to grow silicon nitride and make devices out of it. But silicon nitride doesn't have a Chi2. It only has a Chi3. So we took some inspiration out of this work that was done at the University of Oregon by Mike Raymer's group, where they actually demonstrated quantum frequency conversion using a Chi3 medium. So it was a photonic crystal fiber. And what they demonstrated was the frequency conversion of heralded single photons. So they just sent in their heralded single photons along with two pumps. The pumps were at different frequencies, and those photons got translated by an amount equal to the difference in the two pump frequencies. And that's this four-wave mixing Bragg scattering process that I'll be referring to. So in our case, our devices are these silicon nitride waveguides. And so the types of frequency conversion processes that we've been looking at are the following. We've been looking at the case of intraband conversion. So the idea here is maybe we have two pumps in the 1550 band that are separated by maybe a few terahertz. And that can take light in the 980 band, and it can allow us to either frequency upshift it or downshift it by an amount equal to this pump frequency separation, so just a few terahertz. On the other hand, the flexibility of the four-wave mixing process, right? So in three-wave mixing, your input and your output frequencies define what the pump has to be, basically. But in four-wave mixing, it's the separation, it's the difference between the two pumps that determines the spectral translation range. And so what that means is that you not only have this kind of intraband conversion, but you can also look at processes where you have two pumps that are very widely separated in frequency space. And so, for example, that can allow you to take a 980 nanometer input signal and down-convert all the way to the telecom band, or vice versa. You can take a 1550 input signal and up-convert all the way back to the original 980 nanometer band. So these are the different processes that I'll be describing. And we initially tried to do all of this in waveguides. You know, it makes sense. Why don't we try waveguides first? They're a little bit less complicated than resonators. But the basic issue is that if you look at the effective nonlinearity in silicon nitride, it's on the order of 1 inverse watt per inverse meter. And so what that means is that in order to get efficient conversion, we need to have pumps whose peak powers are on the order of a watt or so. And the reason why this is an issue for us is that the photons that we want to frequency convert, if they're coming in from quantum emitters, they maybe have a duration that's nanoseconds long. So if you're going to use kind of picosecond pulses or some kind of pulse light with sort of watt level peak powers, that's only going to frequency convert a very, very small fraction of the overall, temporal waveform. So that for us put a premium on trying to have efficient frequency conversion with continuous wave light, hopefully relatively low pump powers, and that's why we decided to pursue this in resonators. So the overall prescription for getting these frequency converters to work in resonators is just kind of as I described a little while ago. So we first worry about this phase matching or the mode number matching criterion. And so what that says for us is that the mode number for the frequency converted idler should equal the mode number for the input signal plus the difference in the mode numbers for the two pumps. The corresponding frequency matching condition is just the same thing but looking at frequencies. We can write this to first order as a condition on the group index. So this says that the group index in the 1550 band should equal the group index in the 980 band. That's where the dispersion engineering comes in. So we vary the thickness and the width of the waveguide that comprises this ring resonator. And we find a set of conditions for which this difference in group indices is 0. So then we have phase matching and frequency matching worked out. We also worry about competing four-wave mixing processes. I won't spend any time describing this, but we effectively worry about the overall dispersion landscape of the system. And then finally, we worry about getting light into and out of the resonator in an efficient way. And so the reason why I bring this up in a couple of cases is because the most common way that you might think about coupling light into and out of one of these ring resonators is to just take a waveguide and place it right next to it. But the issue is that if you look at the coupling rate, so what I'm plotting here is a coupling quality factor, so it's inverse to that coupling rate. It really varies quite a bit over wavelengths. So there's something like a 2 orders of magnitude difference in the 900 band versus the 1550 band. And that's because the reason why light couples, or the way that light couples between this waveguide and this resonator, it relies upon things like mode overlap and the phase velocities of light going in that resonator and going through that waveguide. So it's something that can be highly dispersive is basically the point. So what we ended up doing is playing little tricks like taking the waveguide and bending a section of that waveguide around the ring. That gives us an additional free parameter. That gives us the interaction length as an additional free parameter. And as a result, we can tune the coupling so that you can have equal couplings in the two wavelength bands of interest. Okay, so now I'll just show a little bit of data. So we start by just characterizing these devices classically. So this is the case of intra-band conversion. We have two pumps in the 1550 band, an input signal in the 980 band. So this shows the data. These are the two pumps in the 1550 band. The total pump power is maybe about 30 milliwatts. And now the input signal in the 980 band, it gets strongly depleted and you generate these two first order idlers. So these are the frequency converted idlers. And the conversion efficiency into either idler is about 25%. The two idlers are nearly symmetric because they're both equally well frequency matched and phase matched. So you have to break that degeneracy if you want one of them to be higher efficiency than the other one. The other thing that limits the efficiency of this system is that if you pump a bit stronger, it turns out that the pumps themselves start to mix with each other. And so because of that pump-pump mixing, you actually generate these higher order idlers, and you're no longer putting more light into the idlers of interest. But nevertheless, you can frequency select one of these two idlers, and you can say that the overall conversion efficiency is about 25%. We can look at this conversion efficiency versus pump power and compare it to these simulations that I mentioned earlier, and you can see some good agreement. So the simulations really capture the full physics of the pump-pump mixing and the multiple idler generation and all those sorts of things. Okay, so now that we've done this sort of characterization of the frequency converter using classical light, we want to do an experiment where we really send quantum light into this frequency converter. So our experiment is as follows. We have a separate sort of quantum light generator chip, and then we have our quantum frequency converter chip. Our quantum light generator is just producing correlated photon pairs. So this is through the process of spontaneous Fourier mixing. You generate this kind of purple photon and this pink photon that are produced at exactly the same time, and so they're correlated at a level that you wouldn't have for classical light. And so we can measure that correlation between these two photons, and then we can take the purple photon and send it to our frequency converter and shift it to a red wavelength. And then we can correlate this red photon that's been frequency converted with its original partner, this pink photon, and see how that level of non-classical correlations corresponds to the level of non-classical correlations in the initial source. So the other thing that we can do is that if this frequency converted red photon, if it's close enough in frequency to its partner in the pink, then we can actually try and interfere those two photons in a quantum mechanical sense and try and understand whether we see that quantum interference. So this is a little bit about the photon pair source that we developed. It's a simple ring resonator with an access waveguide. And the process, again, is this spontaneous Fourier mixing. So two pump photons get annihilated. You generate signal and idler photons whose frequencies add up to twice the pump frequency. And they're produced at the same time, so they have a level of correlation that exceeds what you would have for classical light. This is sort of what a depiction of what the cavity mode spectrum looks like. So you have these series of resonances. And so what we can do is we can pump on, say, one of these central resonances, this green arrow, and then we can generate photon pairs where the signal and the idler are upshifted and downshifted with respect to that pump. And so, for example, we can choose this sort of pink line and this purple line, which are maybe 3 FSRs above and 3 FSRs below the pump. And so this satisfies both our frequency matching and our phase matching, or our mode number matching criteria. And this is what the spectrum of the spontaneous Fourier mixing looks like. So you generate all these different photon pairs, and we choose one set of photons. So we choose this purple signal and its accompanying sort of pink idler. So the experiments then are that we can first measure the line width of these photons. So that's straightforward. And what we can see is the line width of the photons are a few hundred megahertz. So a few hundred megahertz corresponds to what the cavity quality factor is, essentially. And then we can do a correlation measurement. So we can correlate or do coincidence counting to look at the coincidences we get when we detect the signal photon and the idler photon. And again, because these are produced at the same time, we should have this strong bunching associated with this kind of source. And so we do that measurement, and what we see is that indeed we have this strong bunching where the level of the bunching exceeds what you would have for a classical source. Like a thermal source would be 2 would be that number. So then we look at frequency conversion using this kind of photon pair source. So the idea is that we're going to take the signal photon that's shown here in purple, and we're going to send it into our frequency converter, and that's going to change its color. So now we're going to have a pink photon coming out. And so we do that. We send the signal into the frequency converter, and it gets strongly depleted, and we generate, again, this upshifted and downshifted idlers. And we can select for one of the two idlers. So we select for this upshifted idler. And then we can do our correlation measurement. So we can take the upshifted idler and correlate it against its original partner photon. And what we see is this plot here. So the red shows the level of the coincidence to accidentals for the frequency converted light, and the blue shows the original source. So what we can say here is the level of the non-classical correlations is sort of maintained, at least to within sort of our measurement error. Okay, so then the next thing that we look at is, okay, if the photons, if the photon that I'm generating here, if this frequency converted photon is close enough in frequency to this partner idler photon, then maybe we can interfere them together. So the idea is this so-called Hongu-Mandel interference, right? And the notion is that if you really have identical photons impinging upon this beam splitter, then they should exit together through one port or the other port, but they shouldn't exit individually through both ports. And the reason that is that if you look at these two combinations, the transmit-transmit and the reflect-reflect case, they have probability amplitudes that have a different sign. So these two cancel out, and you're left with this sort of scenario. So if we think about how we can measure this in coincidence counting, the idea then is that you try and measure coincidences between the two exit ports of the beam splitter, but if the photons are always exiting through one port or the other, then you should see a suppression of coincidences. However, if the photons are distinguishable, then you'll continue to see photons exiting through both ports, and you'll see some coincidences. And so that's the basic measurement. So schematically, again, the way this works is we have our initial purple signal photon. It gets frequency converted to the red, and now we're going to interfere it against its partner idler. And we can control the polarization of one photon with respect to the other, and we can control the delay with which these two photons arrive on this beam splitter. So then what we see in the data is that indeed when the two photons are copolarized such that they should interfere, the coincidences go away. When they're orthogonally polarized, we continue to see coincidences. And then we can look at how the visibility of this interference changes as we change the delay for when these two photons arrive on the beam splitter, and we get some kind of agreement with theory. So this basically says that, okay, we can actually make indistinguishable photons using this frequency conversion interface. Okay, so the last thing that I'll say about frequency conversion before moving on to a different topic is that you can use this frequency conversion, as I mentioned earlier, not just for the intraband case where we're shifting photons by, say, a few nanometers or a couple of terahertz or whatever it is, but you can also use it for this interband case where you're really shifting it over many hundreds of nanometers. So in this case, we've just done only classical experiments here, but what we've done is the following scenario where we have pumps in the 980 band and the 1550 band. We take our input signal, it's in the 980 band, it starts out at this black horizontal line, and we send everything into the microring resonator. And when we do that, the signal gets strongly depleted, and you generate this idler in the 1550 band, and the conversion efficiency in terms of photon flux can be as high as about 60%. And so it's actually higher than what it was in the intra-band case, just because with the pumps so widely separated, you don't have this pump-pump mixing, and you don't have as many competing Fourier mixing processes to worry about. You can also do the opposite thing, which we've done. So you can also upconvert from the 1550 to the 980 band, and as you might expect, the efficiency is identical. So what we want to do now, what we haven't done quite yet, is to really apply this to quantum light sources. Okay, so you can think about, can you directly integrate the quantum light source together with a frequency converter? In this case, with these photon pair sources, it's pretty straightforward because they are actually made out of the same silicon nitride thickness. So there's nothing that would, in principle, prevent you from integrating these two things together on the same chip. In practice, one thing that's very challenging is all the spectral filtering that's associated with these kinds of experiments, and we need to implement all of that on the chip as well. It's difficult to do that with low loss and very high extinction ratio. So you can also think about implementing the deterministic quantum light sources. So just as a reminder, photon pair sources are fundamentally probabilistic. So if we really want to be in a scenario in which we're generating only one photon per excitation pulse, at most, we're typically relying upon a situation where you pump very, very weakly. So the most probable outcome is that you actually don't generate any photon pairs per pulse, and then every once in a while you generate one photon pair. And then you can herald it, and you can go on from there. But in contrast, a deterministic quantum light source based upon something like a single quantum emitter, if it has a high radiative efficiency and a high excitation efficiency, then every time you promote the system into excited state, in principle, when it relaxes back down to the ground state, you should get one and only one photon. And there's no trade-off. There's no fundamental trade-off between the brightness of the source and the suppression of multi-photon events. So within the community of sort of researchers who work on indium arsenide quantum dots, the last few years have been quite exciting because there's really been a demonstration that these sources can work very well. And so what I mean by that is that you can kind of characterize these sources in terms of a few metrics. There's the brightness of the source, so that's kind of the probability per excitation pulse that you generate a single photon into a useful channel, so something like a single mode fiber or a single spatial mode in free space. There's the suppression of multi-photon events, so really generating one photon and only one photon, not two photons. And then there's the indistinguishability of the photons, whether the photons are really identical such that you can really interfere them on a beam splitter. And so what's been recently shown by these groups, for example, the group from CNRS, is that they can make sources whose indistinguishability and multi-photon suppression is as good as the best parametric downconversion sources, but the brightness is maybe a factor of 20 times larger. So that's quite exciting. It doesn't happen for every quantum dot. It's still something that's very difficult to do, but there's at least some existence proofs. And then groups like the one from China at USTC have applied these quantum dot single photon sources to this boson sampling protocol. It's effectively a type of quantum simulation that involves networks of waveguides relying upon quantum interference on a chip. And what they've basically shown is that in using quantum dot sources, they can get much higher sampling rates than what they can do if they use spontaneous parametric downconversion sources. So it was thought that maybe this could be a path towards showing this so-called quantum supremacy, where you have some quantum speed up with respect to classical. Recently, there's been some theory that says that this is harder to do than people initially thought. But I guess the point here is that the quantum dot sources can potentially do much better than things like parametric downconversion, or by extension, any of these other types of probabilistic sources. Okay, so one thing that was interesting from our perspective, from kind of the device engineering perspective, is that in these experiments, the quantum dot source was completely held separate from the boson sampling circuit, and so maybe there would be some benefit if you directly integrate these things together in terms of reducing all of the losses. Here you have to take the photons coming out of the quantum dot and the cryostat, couple it into an optical fiber, then send it into this waveguide network. So I don't really have very much time to talk about this in detail. I guess what I'll say is that, in principle, there's nothing that says that you can't physically integrate these systems together. It's just a question of getting the electromagnetics to work out in an advantageous way. And what you really want to do is you don't want to lose the nice properties of the quantum dot source on its own or the silicon nitride photonic circuit on its own. So what I mean by that is, for example, for a quantum dot source, one parameter that's really important is something called the beta factor, or the spontaneous emission coupling fraction. And what this means is that when the quantum dot radiates, right, if it's just in bulk, it's radiating in all directions and you're not collecting very much of that light. So when you put it in a waveguide, what you're really trying to do is you're trying to get all of that emission to go into a single guided mode of the system. And so the reason why this works really well in gallium arsenide is that it has a very strong refractive index contrast with respect to air or silicon dioxide, because it has this really high refractive index. So the point here is that silicon nitride is still a good material for integrating with gallium arsenide, because if you look at this waveguide cross-section, the silicon nitride with its index being around 2, it's still pretty low in comparison to the gallium arsenide index of around 3.5. And so in simulation, you can still get very high beta factor. It's going to be in excess of 90%. So you're still able to be in this scenario where when the quantum dot radiates, it radiates most of its emission into a single guided mode of the system. You can actually also achieve strong coupling for people who are interested in that sort of thing. The other thing that you can do in this system is you want to make sure that once the quantum dot radiates its light into this fundamental guided mode, you want to make sure that you transfer all of that emission into the silicon nitride circuit with a high efficiency, right? And those are going to be the things that make this overall platform more efficient than what's been done so far. But fortunately, these types of couplers are very common in integrated photonics. What you basically do is you just taper down the width of the gallium arsenide waveguide, and for the underlying silicon nitride waveguide, you taper up its width, and that ensures that the phase indices can actually be equal. So when the phase indices are equal, you can have power transfer between the two waveguides. So that's what's shown in this simulation, where light that's initially in the gallium arsenide waveguide gets transitioned into the silicon nitride waveguide, and theoretically, this efficiency can be quite high. So we make these devices. I won't go into details about how we make them, but this is an example of a gallium arsenide ring resonator with quantum dots inside it. It's coupled to a gallium arsenide bus waveguide, and underneath that gallium arsenide waveguide is a silicon nitride waveguide. So you put this inside a cryostat, you pump from the top, you collect the single photons that are emitted by the quantum dot in the ring. They get coupled into the gallium arsenide waveguide and then transitioned into the underlying silicon nitride waveguide, which we outcouple with an optical fiber. This just shows that you can get anti-bunch single photon emission in this system. We can measure the coupling efficiency between the layers, and it's greater than 90%. And you can see kind of cavity QED effects. So you can be in the scenario where you have your cavity resonance and you have your quantum dot line. And when you tune the two onto resonance, then you shorten the lifetime of the quantum dot by about a factor of 4. And so this is the so-called Purcell enhancement, right? This is the enhancement of the radiative rate of the quantum dot due to this modified electromagnetic density of states that you have in a cavity relative to what you would have inside the bulk gallium arsenide. Okay, so I'm going to skip this section on photon pair sources. I put too much in this talk. But what I want to spend a little bit of time on, because maybe it'll be interesting to this community, is the work on frequency combs. So what I'll just say in terms of these sort of quantum photonic links is that these Kerr nonlinear resonators can be an effective way to link different parts of the optical spectrum together. And so maybe you have a quantum system that's operating at wavelength A, and you have a quantum system that's operating at wavelength B. You can use things like quantum frequency conversion, or the thing that I didn't show, which is an interesting photon pair source where one photon is in the visible and one photon is in the telecom. You can use this as ways to link these different quantum systems together. Now, if we look in the classical domain, frequency combs really serve as a way that you can link different portions of the classical frequency spectrum in a phase coherent way. And in fact, frequency combs don't just link different parts of the optical spectrum together, they actually link the optical to the microwave. So what the frequency comb is it's just that. It's this grid of equally spaced frequency components that's produced at the output of your optical device. And as a result of that, you can write the frequency of any one of these components in this really straightforward way. It's just the separation between adjacent comb teeth, this f sub r, multiplied by some integer index n, plus some overall offset with respect to DC. So the way to think about that is that this frequency comb is giving you like a ruler in frequency space, provided that you can stabilize the separation between the comb teeth, so this f sub r, as well as this overall offset with respect to DC, this f sub 0. But if you can measure and control those two frequencies, which are microwave frequencies, so they can be tied to microwave standards, then you have this precise reference. And this reference allows you to measure any unknown optical frequency. It also allows you to synthesize any arbitrary optical frequency that you might be interested in. So the typical picture that comb people look at is this kind of analogy with a gearbox, basically, where you have these two gears and they might be rotating at different angular frequencies, but they can be phase locked together through this chain. In our case, the different angular frequencies are the microwave domain and the optical domain, and the thing that links them together is the frequency comb. So there's lots of different applications for frequency combs, for clocks, for coherent communications, for spectroscopy, calibration of observational astronomical tools, for precision timing and synchronization. And there's really been this really kind of interesting evolution of these devices. So 40 years ago, there are these frequency chain labs at NIST that took up the whole building, basically. And then in 2000, we had the advent of the self-referenced frequency comb at JILA and at Max Planck, and this sort of beautiful thing that won the Nobel Prize, and it brought this down to the tabletop scale. And then for the last 20 years, there's been the advent of these fiber frequency combs that are now bringing things down to the rack mount instrument scale. And we and many other groups throughout the world are now looking at these microresonator frequency combs that ideally bring this frequency comb technology down to the chip scale. And so the overall idea is that all of the different applications and power of frequency combs can ideally now be in a package that's low size, weight, and power and can really exist outside of a lab. That's the hope for this sort of technology. So functionally how this comb works is just the nonlinear wave mixing that I've been describing thus far. So the idea is that you come in with this single frequency input, and what's at the output of the device is this comb of frequencies. So it relies upon processes like degenerate Fourier mixing and non-degenerate Fourier mixing. So come in with a pump, you generate two sidebands that are upshifted and downshifted. Those sidebands undergo their own Fourier mixing, so they create their own upshifted and downshifted sidebands, and so on and so on. You basically cascade out from this initial single frequency pump on either side of it. Now in the time domain, the comb states that are of most interest are ones that are phase stable, and in particular, they're soliton states. So what that means is that you have your initial CW pump that's invariant in time, and what you're producing at the output of the device is really just a single pulse that's circulating inside that cavity. It's what's known as a dissipative soliton, right? So the soliton itself is the balance of nonlinearity and dispersion in the device. And then this is a dissipative soliton because the resonator is always leaking out energy, but it's always being driven at the same time. So you have the balance of nonlinearity and dispersion, the balance of dissipation and driving, and that's what allows you to set up these solitons in these kinds of devices. So we have this project together with Scott Papp and Scott Diddams at NIST Boulder. This is part of the so-called NIST on a Chip program. And the idea is to really try and develop the science and the technology and the applications of these microcombs, understand the various elements that are needed to develop them, so the design, the fab, the measurement. And what we're really focused on are combs that can be fully stabilized, right? So by full stabilization, what I mean is that if you have this comb of frequencies, you want to stabilize not just the separation between the comb teeth, but also the overall offset with respect to DC. And so for us, this put a premium on generating combs that can span one full octave in frequency space. And the reason for that is that the most common way to measure this offset frequency is something called F2F self-referencing, where you take a low frequency component of the comb, you double it, and you compare it to the corresponding high frequency component of the comb. And just through some simple algebra, you can see that if you do this comparison, the beat note that's generated in this F2F scheme is just the offset frequency. So it's this really kind of powerful and elegant way for measuring this offset frequency, but it imposes this severe requirement. You need a comb that can span over one full octave in frequency space. So what we've been trying to do are to develop these combs that span an octave in frequency space and then apply them in a couple of different scenarios. So in particular, we're interested in things like optical frequency synthesis. So the idea here is you have this really good tunable laser whose output is very precise and very accurate at the hertz level, essentially, because it's referenced via these fully phase stabilized frequency combs. So the idea is that you can come in with an RF reference input, maybe it's something coming from a hydrogen maser or whatever it is. The comb then phase coherently multiplies up to the optical domain, and now you have that reference in the optical domain, so you can take your output laser, you can beat it against that reference, and then you can make changes if you need to change the frequency of that output laser. We also are interested in the opposite sort of thing, so clocks basically, where you take an optical input and you stabilize that to some atomic system, let's say, and then you use the combs to phase coherently divide down to a countable RF frequency. So both of these things, both clocks and synthesis, can be done with the frequency combs. So I won't go into very much detail about how we develop these devices. I'll just say it involves a lot of the ingredients that I've described so far, things like dispersion engineering, worrying about coupling light into and out of resonators, and being able to simulate what the comb spectra are going to look like. And so these are the types of combs that we've generated. So these are now octave-spanning microcombs. So in this case, they're pumped at 1550 nanometers. They go from about 1 micron to above 2 microns, so they span over 1 octave. This is another case where we pump at around 1064 nanometers, and the comb goes from about 785 nanometers out to above 1600 nanometers. So these combs, again, they're all relying upon this generation of soliton pulses inside these ring resonators, and they produce these huge spectra. And so, again, I won't go into this in very much detail, but what I'll say is that the physics of this damped-driven nonlinear system is such that in addition to these really nice soliton states that are the things that we want to use for metrology, there's also kind of noisy, chaotic states that you want to avoid. And so a lot of our work, both theoretically and in the lab, has been on trying to understand the trajectory through phase space, so what experimental knobs you tune in order to avoid these chaotic states and land into these soliton states. And you have to worry about things like thermal effects. So the fact that when you put light into your resonator, some of that light gets absorbed, the refractive index changes, and that shifts all the cavity modes. But we've worried about these sorts of things, and we can get some reasonable agreement between our theory and our experiments. Okay, so now just to end, we spend the last 5 minutes mentioning 2 of these applications that I referred to earlier. So one of them is on optical frequency synthesis. We're part of a DARPA project called Direct On-Chip Digital Optical Synthesis. And what DARPA wants is a widget. So they want this thing that consumes less than a watt of total electrical power, fits within 1 cubic centimeter of volume, and it needs to produce optical frequencies with hertz level accuracy and hertz level tuning, and this sort of relative instability that scales as 10 to the minus 13 over the averaging time. And so the way that this has to be done then is to use fully stabilized combs. You really say that, okay, I'm going to have my laser output, and it's going to be phase locked to an RF reference because I have these fully phase stabilized combs that are serving as the reference. So we're part of a large team that's working on this project. It involves Santa Barbara, our colleagues at NIST, Caltech, EPFL, Virginia, University of Virginia, and the company Orion. And we have some scheme for doing this. We have a tunable laser whose frequency gets locked to a pair of microresonator frequency combs. We actually use a pair of combs as a way to solve some of the power constraints that DARPA imposes on us. And I can give more details if there's interest. So these are some of the chip-integrated technologies that are involved. There's lasers coming from Santa Barbara and Orion, silica combs coming from Caltech, silicon nitride combs that are coming from us at NIST. And then in Boulder, they've done a really nice kind of lab-scale demo where they've linked up all these integrated photonic components using optical fibers, and they've been able to do frequency synthesis. So this is an example of the fully stabilized microcomb spectrum. So it extends over 1 full octave. This is 140 terahertz to above 300 terahertz. This is the output tunable laser scanned across the telecommunications C-band. It's referenced to underlying comb teeth. This is an example of stepping the output frequency of the device in kind of 15 hertz increments. And then this is an example where the output frequency of the device is now compared against a completely independent self-referenced frequency comb, so kind of a traditional frequency comb. And you can kind of see hertz level accuracy in terms of this output optical frequency. And so then they've also done this kind of nice artwork showing that you can write out NIST. But the sorts of things that you might want to do with these kinds of synthesizers are not just write out NIST, but look at things like precision LiDAR, coherent communications, and so on. So what we haven't done yet is put all this into a really small package that's less than a cubic centimeter in size, and those are the kinds of things that we're trying to do going forward, and it's extremely challenging. I'll say that for sure. Okay, so the final thing about clocks is that we can think about the clock as operating kind of in the reverse regime. So instead of taking RF and synthesizing up to the optical, we take optical and we divide down into the RF. So again, we're part of a DARPA project here. This is called Atomic Clocks with Enhanced Stability. DARPA really cares about portability and low size, weight, and power. So they want this thing to take up less than 250 milliwatts of electrical power, exist within 50 cubic centimeters. And they worry about the drift of the clock. They worry about something called retrace, where you turn the clock off and you turn it back on. You want to make sure that it reads the same value. And so what we're doing, what our team is doing, again, this is a big team involving Draper and NIST and Caltech and Yale and Stanford and the Swiss company Ligentech, is we're doing 2-photon spectroscopy of rubidium vapor. So this is at around 385 terahertz. This transition, this 2-photon transition, is at least somewhat environmentally insensitive and can be measured with relatively low power. You then use these combs to phase coherently divide the 385 terahertz signal down to this countable RF frequency, so down to about 10 gigahertz. So these are some of the chip components involved. Again, the combs. There's vapor cell spectroscopy being done at NIST Boulder by John Kitching's group. These are these kind of small form factor MEMS vapor cells that his team has pioneered. And then these are some examples of clock demos. So they show kind of frequency instability that scales as 4 times 10 to the minus 12 over root tau. This shows the retrace, where you basically say that the output frequency doesn't deviate by more than a part in 10 to the 11. So one important point, and then I'll start to wrap up, is that for this type of application, I mean, we're really constrained by the things that DARPA wants in terms of power and form factor. But in Boulder, they've actually recently done a really nice experiment where they've taken a cavity-stabilized laser and used these combs to divide down. And they've shown that the combs themselves support frequency instability at the 10 to the minus 17 level for a few thousand seconds of averaging. So this isn't quite the best performance that you might need for like a 10 to the minus 18 atomic clock, like the strontium lattice clock or whatever it is. But this really shows that the combs themselves can support really very sort of high-level performance in terms of clocks, and in this case, we're really limited mostly by the vapor cell spectroscopy. And again, this sort of lab demo was photonic chips strewn across optical fibers in the lab, and so what we need to do in the future is really see all this come together in this really tightly integrated package. Okay, so with that, I'll stop and just want to acknowledge the people that have done this work. So Ching Li is really an outstanding postdoc in my lab, worked on both the frequency combs and the frequency converters, together with Shi Wen and Anshuman. Shi Wen is also developing photon pair sources, Anshuman some quantum dot work. Marcel is another staff scientist at NIST who's pushed all of the quantum dot heterogeneous integration. We work a lot with Darren Wesley, who fabricates the combs, Scott Diddams and Scott Papp from NIST Boulder and their team. A bunch of people on these frequency synthesis and clock projects get these very nice detectors from Sei-Woo Nam and colleagues at NIST and Boulder. And thank the people who help support our research. So thanks for your attention. Thanks for coming, and I can take questions.